smaller volcanoes, we call them monogenetic volcanoes, which only erupted once and then never erupted again. There's one here in this view we can see here. These are more limited in usage. We didn't spend a lot of time on them, but they give small amount of ancillary information. But predominantly the information was based on the big coastal volcanoes. Now in the coast, because of the action of the sea and also ice, the volcanoes are carved into very nicely and they form these wonderful cliff sections. The cliffs are typically about 500 meters to perhaps 1,500 meters high. They're very impressive cliffs and they extend laterally at least a few kilometers and sometimes 10 or 15 kilometers. The quality of the exposure is actually quite important. It's extremely good because we're in a very cold environment and we don't have what I like to call the obscuring effects of vegetation. So the rock is very clean. On top of that, again, because of the very cold environment, you don't get the weathering effects that you're more likely to get on volcanic rocks in lower latitudes and warmer climates. Now you might think working on cliff sections such as this could be, to say the least, challenging, and at a distance it looks like that, but in fact these are wonderful sections to work on. The information is second to none. It's superb. And now this is an example. This is the map I produced of this part of this cliff here, and you can see you can actually attack these cliffs by working up gullies. You can get many hundreds of meters up. It looks more steep than it is basically. It is very steep in places, I admit, but in fact it's not particularly dangerous working up to this kind of level, 200 or 300 meters up. You can also work on ridges and do sections there as well. You can then fill in the gaps with binoculars and helicopters and such like, looking at the rock face. You can get wonderful information to reconstruct these volcanoes and deduce environmental information. So at the start of this work, what was the outcome that you anticipated? Well, we thought this is a straightforward problem. The hypotheses are black and white in this respect. They're very focused on when this single transition took place. Either it took place at 14 million years ago, or it took place quite recently, about 2.5 million years ago. And if I map onto this here, the age of the volcanic rocks that we'll be looking at, they extend between about 2 million years and 11 or 12 million years. So you can see there are strong contrasts in what we expected to find. On the one hand, if the stabilists were correct, we'd expect to find evidence for only cold ice throughout the entire section from bottom to top. Whereas if the dynamists were correct, we'd expect to find overwhelming evidence for warm ice conditions, except right at the top of the column in the youngest rocks when we should find a transition into cold ice. So that it looks like a very straightforward problem, and this is one of our major targets to determine the timing of the age of this very rapid, sudden change in thermal state. And what did we find? Well, here's a summary of the results. You can't read the details, please don't worry about that. It's a very simplified summary of all their results, and please note that for most of the localities here, whose names you probably won't be able to read, there are multiple sequences with multiple ages there, so there actually is a wealth of data in this section here. So I can summarize the thermal conditions which we found at these localities. These are the localities for which cold frozen bed conditions were evident, and these are the localities at which warm thawed bed conditions were evident. Now, it's obvious that as you go up the column from the bottom to the top here, the evidence for cold-based conditions becomes more frequent, and it looks like the climate is getting progressively colder, at least in terms of the ice conditions. But similarly, we're finding warm ice conditions surprisingly young in the record. They keep persisting, they keep popping back, although they are getting fewer, which indicates, again, the climate is getting colder. The important thing is that the overall picture here is utterly dislike any of the two records that we'd expect to find. This record here, which I'm showing, stabilists on the left, dynamists on the right, they are nothing like what the truth is on the ground. The answer is there is no single step change. On top of that, it's unrealistic to assume that on the basis of this work on the eastern Mars and the Transantarctic Mountains, there's no reason to assume that the entire ice sheet in East Antarctica switched from cold-based to warm-based or wet-based, time and time again. And the pattern and that rationale indicate this is a polythermal ice sheet. Now, we looked around for ways to verify this. And I'd like to show you this cartoon. Many of you may have seen this. It's one which NSF in America produced about 7 or 8 years ago in response to increasing discoveries of lakes beneath the East Antarctic and West Antarctic ice. Now, the presence of lakes, that's water beneath ice, indicates that at least parts of the East Antarctic ice sheet were wet-based. Similarly, more recently, we've been getting some very increasingly sophisticated modeling of the thermal state of the entire Antarctic ice sheet. This is just one I have chosen here. I could show show you several others. And if we look at East Antarctica here, what we're interested in is the areas of red relative to the areas of blue. Red areas are places where there's a likelihood of basal melting. The blue areas are areas where it's cold ice. And you can see more than 55% of the entire Antarctic ice sheet is at pressure melting point. It is likely to be wet. Even the East Antarctic ice sheet is affected. It is a polythermal ice sheet. So in summary, we know that from the geological record, the East Antarctic ice sheet changed its thermal regime over time. And the hypothesis arose it was a single-step change. Unfortunately, the traditional methods of examining the thermal state of the East Antarctic ice sheet were completely unable to determine when this took place and how it took place. So by looking to the volcanic record, we're able to demonstrate quite clearly that we have an alternation, unexpectedly, an alternation between cold-based ice and warm-based ice, which recurred time and time and time again. There is no evidence for this hypothetical single-step change in thermal regime. In other words, the Antarctic ice sheet was and remains a polythermal ice sheet. And unfortunately, it'll be very hard to model. So whilst I would say with our result here, we've made at least 2, if not 3 steps forward, unfortunately, from the modeling side and predicting the future, we've probably stepped 1 back because it's actually very hard to model a polythermal ice sheet. I'll stop. Thanks very much.
Thank you very much. That was a great talk. We're going to open for a question session. We have 15 minutes. You are definitely on time. Thank you very much for that. So my first question that I got was, how common volcanic sequence are in the Antarctic? So little of the surface is exposed. If you got that, there was a little bit.
In terms of, okay. Sorry, in terms of rock exposed, because most of the sequences I worked with in Victorialand were coastal sequences, there's quite a lot of rock exposed. If you're looking vertically down from a satellite, you wouldn't see these cliffs because they're more or less vertical. But there's actually a lot. I don't know what the proportion is, whether it's 5 or 10%, which sounds very small, but there is ample to actually get a very detailed story out of this. The work we've done, because the access is actually extremely difficult at some of these volcanoes, I would still regard as a little bit better than reconnaissance, what I tend to call detailed reconnaissance, and I would love to be able to spend many detailed seasons working on just 1 or 2 kilometers, but you can't do that. But there's a lot of rock